we are going to be arranging meetings in Silicon Valley. I want you to think pitch days, but with the Silicon Valley leaders. But rather than pitch them, because I hate pitches, we're just going to book out a table at the Rosewood, and we're just going to have like 15, 18 of us there. And we're just going to have like 3 hours, 2-3 hours there to all get to know each other. And what we're going to be doing, we're going to be looking for people who are raising a minimum of like $10 million. And again, with regards to why we're looking for that, is that we think that if you're not respectfully looking to raise at least $10 million, and even that I would say is on the low side, it's not actually going to be something that is scalable. And actually, I want to say one thing, just for the people that have just joined now, Celine, Marina, Christine. I've got to say, great to see you here. So thank you all for joining. Christine, as always, good to have you here. I hope you're well. Real one, great to have you here as well. And yeah, so okay, people entering now. So what we're going to be looking to do, and I want your feedback on this. All of you can actually go away, tell us your opinions on it. We're thinking we're going to do it. We're going to basically charge a commission only on success, right? So what that means is that for any of you that are looking to raise a minimum of $10 million, we're going to launch something which mimics an accelerator, whereby you will work exclusively with executives from Silicon Valley who know the Silicon Valley VC world inside and out. And it's not going to be structured in the way that like a Y Combinator, where it's like turn up every day at this time. I don't like that. I think there's only so much one can do for a founder. And what we're going to do is essentially just say the resources are there available to you, and the structure will be this. One, work with our executives. Again, there's no cost to you. Work with our executives to prepare yourself so that you are good enough to actually pitch to the top VCs in Silicon Valley. Two, we need to teach you how to make sure you position yourself appropriately and focusing on what is actually relevant and important. And then in addition, where the moat is, what we're going to be able to do is guarantee for the right founders is we're going to be able to guarantee that you have direct access to energy and direct access to GPUs. So whilst all of your competitors are scrambling and fighting to actually make sure they can even access GPU capacity, we're going to have it already ready to go in our own modular data centers. And again, like when we started Rayon, the whole point was to build a supply chain and help you guys build multi-billion-dollar companies. We are now at that point. So the next steps are Tarek's going to put together a form for all of you to fill out. You will automatically also be going for the Rayon prize, which is our annual prize for companies, not just startups, actually, for companies. And then it is down to you. If you want to work with our executives, you can. They will help make sure that you are ready to pitch to the Silicon Valley elite. Once you get the opportunity, we will invite you out to Menlo Park. Most likely it will be at the Rosewood, and then we're going to just sit around, have a few drinks, and just get to know each other. So great to have you all here. Risto, honored to have you here. And I've got to say, Risto, whenever I think about working with the Silicon Valley elite, you always come to mind, and I genuinely mean that. So good to see you.
Yeah, good to be here.
Good to see you, sir. So yeah, I don't know how much of that you caught, but I'm perfect. So look, I mean, the reality is that there's no shortage of capital right now, but there is a bottleneck. And, I almost feel sorry for the VCs because it's hard for them to know exactly where to allocate that capital. Gene, good to have you with us as well. I'm going to pass it over to Leonidas Tam, but just beforehand, a huge thank you to our sponsors at OVH Cloud. Again, Tarek will share the link in the chat. And again, as always, there you go, Tarek, thanks for doing that. Please do make sure you sign up for the 100,000 euros in free cloud credits. Again, I wanted to reiterate, this is actually going to be our last online event for the summer, and then we will pick back up again in September. Otherwise, we will be doing in-person events across the summer as well. So hopefully see you all there. And with that, I'd like to introduce Leonidas Tam and hand it over to you.
Thank you. That was a really nice set of announcements, and that seems really exciting. I'm based in the Bay Area, so we have a co-working office in Palo Alto and another co-working office in San Francisco in the Ferry Building. So I'd love to see anybody on the call and meet you and welcome you guys here. I feel like I would have to play host, given that you're kind enough to attend my presentation. So yeah, I was previously a research scientist at NVIDIA, and we left with a couple of NVIDIA guys to start our firm. The basis of our firm was based on transformer technology. It started around 2021, so this is just before the advent of ChatGPT. I think our thesis was proven correct in that we bet heavily on this technology. So sort of the prompt that Lawrence gave us is the future of quantum computing. And I want to approach this through the way we approach technology, and definitely the way we approach technology at NVIDIA is, and previously I was at Stanford, is to deeply understand the technology, work with it. I was working with Professor Jeff Ullman at Stanford, and in 2014, that's when we were really starting the deep learning revolution. In that case, he wanted to tackle actual projects. So the project we worked on there was a diabetic retinopathy, a computer vision project, and that's sort of where I cut my teeth on things like convolutional neural networks for computer vision, things that people know really well now. With that said, the structure of this talk is Lawrence encouraged me to keep it accessible, to keep it sort of compressed, not to have a very extended talk. I'm going to be presenting our work that we published at the ICLR, the iClear Foundation Models and Science Workshop that we presented there. And we had another more theoretical paper, but this one is more a sort of engineering and practical study, so it's more appropriate for this audience. And yeah, without further ado, let me load up the
You have to share your screen? Yeah.
yeah, the presentation. Yeah. Let's see if I can find it here. Oh, okay, wait, window. I gotta click over to window. Okay, can you guys see the window? Yes.
Yes, we can. Yeah, thank you.
Okay, let me enter presentation mode and see if that's even better. So it's full screen, great. So the title of the study was Symmetry-Aware Entropy RL, SARL, for chaos-accurate holographic duals in NISQ hardware. So that is a mouthful, I'm sure. What we'll talk about, and I want to phrase it, is one, I think many of you have heard, well, first of all, what is a quantum computer? I know some computer scientists are on this call. So, you know, certainly those people are well aware of the trends that have been going on for more than a decade in quantum computing. The second term you guys probably have heard is this phrase, quantum supremacy, which means that we've entered in an era or an application where quantum computers far exceed the ability of traditional computers. And by traditional, we probably mean a computer based on something like the von Neumann architecture. So maybe definitely something like CPUs, definitely something like GPUs, where even we're doing parallel processing. So that's hard to imagine, since we know already GPUs are taking what's called a SIMD architecture, single instruction, multiple data. And so they're already incredibly parallel. So why would we expect to do better than GPUs? I think that's a fundamental question. And this idea of quantum supremacy is there are applications where you need a quantum computer. You might say hyperbolic phrases like, if we were to do this classically, that means on a regular computer, or even like a gigawatt computer cluster that we know are being built out all over the world now, it would take more than the lifetime of the universe, right? Like you can make hyperbolic claims like that and with a straight face. So let's the application I'm working on is a very physics-based application. It's this application going to the days of general relativity. My passion, I was trained as a physicist. My PhD was with a medical physicist, and we worked on MRI hardware. This was at Yale University in the Department of Diagnostic Radiology. We worked at MRI hardware, and MR spectroscopy. So manipulating the magnetization of atoms, which is actually very topical to quantum computers. So it's a very natural shift for us. The idea is that quantum computers, you're often manipulating individual energy states of atoms. So I like to say that in quantum computing, you're sort of forcing everybody to be physicists. And I love that. I love that about this field. So that's also something I'd like to share with you guys today. Okay. And yeah, by the way, as Lawrence mentioned earlier, feel free to jump in if you guys wanna add a comment. I know this presentation is about 12 slides, so it's not going to be too crazy. And because of the advent of agentic coding, I also have a little animated learning guide. So 12 slides plus a little bit of an animation to
And
keep
if
things
anyone
up.
wants to just throw their questions, as you guys do every week, please throw your questions into the chat, and I will ask them, well, try to ask them at exactly the right time. So yeah.
Perfect. Thank you, Lawrence. Yeah, the kind of mode of presentation I'm used to in the academic sphere is this idea of a journal club, which is that we're all on this journey of learning, trying to share recent best practices, recent research. So let me just give this briefly. I wouldn't normally take a show of hands, but I think I saw a lot of people in the audience from different backgrounds. So just to set a primer of quantum computing. So we all know computers use something called bits, right? So crazily, they use binary, which is toggle codes, zeros and ones, and these are deterministic. They were, as you guys all well know, they are used in transistors, which is a very fast way of switching these at megahertz speeds. And this is the basis of our computation. We're translating these binary bit strings into things like word processors. So it's already pretty wild, the era that we're in. So instead of using these bits that are so well behaved, and we've spent decades, the semiconductor industry has spent decades perfecting these bits, for perfecting the length scales of these bits. You might have heard things like TSMC manufacturing on 1.4 nanometer. So these bits, these features of these bits are at that level of dimension. And we're going to throw all of that out, and we're going to replace it with something called a qubit. So what is a qubit? So it's this neologism of a quantum bit compressed. So what makes it quantum? So if you remember to your quantum physics, a quantum state, or even in popular science, a quantum state is something that exists in a superposition of two states, and that allows for parallel processing. So we probably need to unpack for that a little bit. So what is a quantum superposition? The most macroscopic thing that demonstration that every freshman physics major sees is sending a photon through an interferometer. And we see that the photon in an interferometer, it'll either go left or right. There's a fork in the road and it'll go left or right. And we don't exactly know which fork in the road it can take. And so that when it's given a choice between two forks in the road, it forms something called an interference pattern. And we say that the nature of that photon was quantum mechanical, in that it is described by a probability. So when you're working with quantum bits or qubits, you're working with probabilities. And computation involves calculating these probabilities. Really, when you start having more than one qubit, is you're working with probability distributions. So instead of a point metric, you can just look at that probability distribution and you see that it's being smeared out in a variable in space, in time, in however dimensions that you're manipulating. And because we're working with these distributions, it's no longer this point estimation. You're acting on a whole space of states in effect. And that is what leads to that parallelism. So hopefully you guys will have some intuition from that. Okay, so let me briefly describe the problem that we're working on. And so you may have heard of two strange things. You know, these physicists are always talking about these strange things. So two of the strange things they talk about are, there's a paper called the ERP paper. It's the Einstein-Rosen-Podolsky paper. It stands for the ERP paper. It's famous because it first described the phenomenon of quantum entanglement, or as they described it, the more popular phrase would be spooky action at a distance. So the idea is that if you have two qubits and there's something called entangled, and you move them apart from each other, you can observe one qubit, and because they're entangled means that their probability distributions are connected. It will immediately and instantaneously cause an effect in the second qubit, no matter how far they are apart. So Einstein hated this. He called this spooky action at a distance. He thought it was non-physical. In the modern world we live in today, we now know that this actually happens. Quantum entanglement is something that absolutely happens and is something that is observed, for instance, in quantum computers all the time. And we rely on this, for instance, using something called a Hadamard gate to prepare a quantum entangled state. The reason why he didn't like this, Einstein didn't like this, because it essentially clashed with his most famous theory, the theory of gravity, the theory of general relativity. And the idea is that he showed in another paper called the Einstein-Rosen paper, is that if it would be possible to have things connected areas of space-time called wormholes, and later these physicists, Leonard Susskind and Juan Maldacena, they describe that maybe these two phenomena are related, that whenever you have quantum entanglement, which, by the way, I should leave as an aside, does not break the speed of light speed limit, because you can't actually communicate. You would actually need to verify it, and in order to verify it, you would need to travel. So it doesn't break the speed of light. So at least that is sacrosanct. The idea is that ER equals ERP, which means that whenever there's quantum entanglement, there's actually a mini wormhole being formed between the two qubits, those what have you, either the superconducting circuit, or in the experiment that we're using, we're looking at, we use a trapped ion quantum computer in the studies that I'll show. So there's this theory, ER equals ERP. And so Juan Maldacena is famous in theoretical physics for saying, he described this thing called holographic duality. In popular science, you might have heard this as, maybe someone like Elon Musk describes it as the universe as a hologram. So so it seems like physics has devolved into, it's just a series of catchphrases. So what is meant by the universe as a hologram is that the universe can be described by its boundary. And so they took a very topological argument. I'm not a theoretical physicist, so I can describe these results as best as I understand them. And so it's a really a mathematical description. And the reason why we like it so much is it allows us to describe the it allows us to describe really large things like the universe, or for example, more typically a black hole, and describe them just by observing their boundary. So black hole boundaries are a lot easier to observe than their interiors, as you well know. And the other aspect of this is that black holes, physicists don't just like black holes for the fun of it. They like it because it is essentially a pressure cooker where we're studying very large effects that usually act on very large spaces, like gravity, which we typically think of as a very long range effect, and quantum mechanics, which we typically think of as a very small effect. Okay.
Can I jump in? Can I just ask? Yeah. Sorry, do you mind if I jump in? I just
please, yeah.
So we've got one comment from James Cape. Great talk. I would like to talk with Leonidas about presenting to the Intel Alumni Network. He can contact me on this email. So first of all, James, absolutely. Tarek is going to make sure he connects you with Leonidas now. I would just ask, and I hope nobody minds me asking this question, but would you mind just giving, like, as high level as possible, what actually is the difference between what scientists think a black hole is versus a wormhole?
So that's a perfect question. So the idea is that a black hole, they're not sure what's inside a black hole. So one of the theories of what's inside a black hole is this ER equals ERP is that perhaps it is a boundary of a wormhole. So that's exactly what we're talking about. And perfect question. And Juan Maldacena, he described that you may be able, because the mathematics that he described, it's something called a dual, which says that we can use a hardware version. In this idea, we'll be using 12 qubits. And that will be mathematically equivalent to a black hole. And so instead of people thought for a long time that physics is dead, because we would have to build these incredible super colliders. For instance, the CERN super collider cost billions of dollars. The success of it was it found the Higgs boson. However, it didn't actually push the field of it didn't inform us about what's inside a black hole. It didn't resolve this question of ER equals ERP. So there's this new enthusiasm in physics, is that experiments on quantum computers, which are a lot less than $1 billion. We're working with them in this study. A lot less than $1 billion is we're able to perform novel physics and ask the question, what is this ER equals ERP? So there was this big Nature paper published by Jafaris et al., where they were trying to design. So the core of this study, I finally got into it, is they're trying to design quantum circuits that are analogs of black holes, microscopic black holes. And by designing these circuits that are mathematically analog to black holes, we can run experiments on them. And it's as if we've created our baby black hole in the laboratory. And so the way they did this is they took I would say, a very straightforward approach of gradient descent over continuous trainable weights, where the weights are the operators of the quantum computer, the different operators that you can use to manipulate the quantum bits. And in our approach, we do something more sophisticated. We take an A3C, which is a reinforcement learning variant, and we use that to walk the landscape of the Hamiltonian. The Hamiltonian, being the energy operator, describes how a system will evolve in energy. And this is exactly what we talked about in the foundations of science, AI and foundation models in science, the AI workshop at iClear, is that what does it mean to use AI models in science? So we all know AI models can hallucinate. So as a very practical case study is, how do we control that hallucination? How do we make sure that we're still doing good science? And I think, Lawrence, you made this point about vibe coding in the beginning, is how do we take vibe coding? I love it because we can say there's an analog here. We described the holographic dual. There's a tongue-in-cheek, there's a holographic dual between using vibe coding to create an enterprise application and using AI in your science to create good science, right? There's a one-to-one mapping there, or there's some mapping there, I would argue. So with that said, let's keep moving. Okay, so first of all, why do they expect that we need quantum computers? I kind of alluded to this earlier. So the idea is that we have things called Majorana. The theoretical construct is a Majorana fermion. So a fermion, you may know, is the description for a particle of spin 1/2, which is the electron. So we all have fermions in our lives, and we're all technologists here, so we all work with a lot of electrons. So Majorana fermions are, you can imagine, a kind of a cousin of electrons. And in this SYK model, they're connected all to each other in what's called an all-to-all system. So this requires a number of terms when you're modeling the system that grows by the order of n to the 4th. And also the Hamiltonian grows by n to the squared. So you have this n to the 4th growth on top of n to the squared growth. So what we're looking at is essentially 12 qubits. It's 2 to the 12th is 4096, and then we have about 500 terms in the Hamiltonian. So it's still computationally tractable with classical computers. So we're going to be in this intermediate regime for experiments where we're verifying our results with classical computing so that we know we're doing good science. The idea, though, is quickly when you get to n equals 50, if you work out the math, you're in this region where you say, oh, you couldn't calculate these with all the atoms in the universe. You know, it's that type of exponential explosion. So what we're trying to, the actual task is we're trying to find simplified all Hamiltonian terms that still preserve the statistics, the holographic dual, the mathematical nature of this, so that we say it's an analog. Okay, so how does our reinforcement learning work? It's a pretty standard reinforcement learning algorithm, A3C, which is the asynchronous variant of reinforcement learning. And what it does is it's crawling this optimization landscape, and it's trying to go to the highest peak here, which we say is this statistic where the energy levels reach equal repulsion, which means that you can just take it as a shorthand that it represents these type of black hole physics. So it needs to search along the Hamiltonian, this energy landscape. It's really difficult because you can imagine an energy landscape has all sorts of minima. So we use something called state entropy regularization, which is a way of kicking it out of local minima in a way that's conditioned on all the different paths that it's taken. And one of the ways we know that we achieve that is people usually, the other way they do this is they try to manipulate the learning rate of their algorithm. So the learning rate is how much you weight these steps in the algorithm. So instead, we found that we had essentially nulled that factor out. And so we found that our constant learning rate maintained exploration. And that's when you have normalized your factor out and you can just have a constant factor, you've essentially removed a hyperparameter in your engineering. And for engineers, they know this is usually a good thing. It means you've essentially removed one of the dials that you're turning, and you kind of want to have fewer dials, instead have it built into the machinery of your operation. All right, this is an idea of how we're doing that. So we have this, we're choosing quadruples of these Hamiltonian terms, and we're having a policy, which is a neural network selecting discrete edits. The edits are something like add, remove, flip the sign, or perturb the value of an operator. In this environment, we're doing exact diagonalization using GPUs. In actually, it's 4096. We went up to 4096 there, and that allows us to find exactly the energy levels and do something called trajectorization, is which we inspect how the system is progressing as we step forward in time. And then we use a whole sort of reward suite. In reinforcement learning, you have to design your reward function very well. So reinforcement learning is this idea is that you take your system takes a step, then it looks at its environment and it computes a reward. So RL is led to such breakthroughs as AlphaGo, AlphaZero, you know, the world-beating chess. It's the same class of algorithms. SpaceX landing a rocket, that is a type of reinforcement learning algorithm. People, computer scientists like it because it. Hopefully, I'm not over describing this for some people who are experts in this already, though, is that it is very much like how humans work, right? Like humans kind of do something, we see if it resulted in something good, and then we change our behavior. So it's something that we can kind of relate to even as we add in all these bells and whistles. So, excuse me, pardon me. At this moment, maybe I'll show a small demonstration of our animation. So let me try to share.
While you're doing that, I was going to say we've got a few questions in the chat, but I'm actually going to leave them to the end, guys, because I don't want to break up the flow, if that's okay. Leonidas, I trust that works for you.
Yes, yeah, absolutely, happy.
Cool.
So yeah, the wonders of agentic coding nowadays. I put together this little animation. So what is the experiment that we're running? So we're looking at different preparations of our 12-qubit quantum computer, and then we're perturbing them with different signals. We're using, in our case, we're using the Alpine Quantum Technologies IBEX quantum computer, one of their computers that they've released, and it's a 12 qubit computer, and it's trapped calcium ions that you perturb with RF pulses, just like you do an MRI. So it's something like I feel is very familiar. So this idea is that we have these, I don't know if you can see these 12 qubits, and they're prepared in different gates. So along this line, we have all these states of the 12 qubits from qubit 0 to qubit 11, 12 qubit. And we can see we're taking 50 time steps. As they're prepared with a Z magnetization along the pole. And with the different operators that are applied, they are taking different trajectories. So we're looking at these, the spin trajectories of these 12 quantum bits. In this diagram, what we're doing is that so each qubit, this system, these 12 qubits, they have I mentioned this, I keep mentioning this Hamiltonian, which I know sounds archaic or esoteric to people, but in physics it's well known. It's this matrix that describes the energy levels. In the 12 qubit case, it's a 12 by 12 matrix, 4,096 terms, or sorry, that's not 12 by 12, it's probably 64 by 64. And we projected that down to this Hamming weight. So this is showing how the state of the qubits are kind of progressing in time. And what we're looking for is that they're dispersed. So for different preparations, they'll be more dispersed. So if we look at, for instance, this other preparation, the M14 preparation, which only looks at 14 fermion terms, we'll see that they cluster more than the M25 preparation. So it's a very statistical, we use all these essentially physics audits to track the statistics of this. And this is how we guarantee the performance of our application. Okay, so yeah, hopefully that gives a more animated intuition to our presentation, to our experiment. And I'm happy to show that again if people want to look at it later. Okay.
Yeah, thank you. Just, guys, we will make, as long as, Leonidas, as long as you're happy for us to, we will share the slides.
Yes.
One round after. Perfect. Thank you.
Happy to do that. Yeah, so the other thing that we can look at is we can look at the geometry of the qubits. The way we prepare the qubits, as we mentioned, this quantum entanglement. So these qubits are connected to each other. And so we find a very different topology when we're preparing qubits that match the statistics for the holographic dual. In this case, we find that the holographic dual, they have hub and spoke characteristics that they kind of cluster into these nodes, whereas networks that lack structure do not describe the target that we want. So this is the more integrable structure, and we find we have a much more amorphous topology. So this is another statistics diagram. We're showing that we have some m equals 12 terms, 12 being Majorana terms, that satisfy these statistics. And then very peculiarly, as we increase the number of terms, so in increasing terms, we would expect it to be more closer to a real system. 12 is actually well known to be it's too much of a toy system, it's too few. And then in between we have, the topology is too amorphous, so it doesn't give us the statistics that we need. And then at 25, we kind of recover a Goldilocks zone where we know that has enough terms to be representative of the physics, but at the same time, it represents the physics and it has enough terms to fulfill our intuition. And this is also published work, so you can look at the paper if you're interested in the full details. So this is this slide is about the idea that we need to, in science, we're typically not satisfied by just statistics, right? And I think this is sort of what you have with enterprise applications. We want, and this is a little bit of why people don't like AI hallucinations, right? And the idea is that you need a causal link. So humans, one criticism of humans is that we love stories, we like narratives. The reason we like narratives is actually for a good reason. Stories have a causal link. They make sense. A implies B, right? And so A implies B implies C, right? So if you don't have this, it's like, what is going on? You're just like a stochastic parrot, which we don't like, is because you're just spouting nonsense. So the idea is in our experiment, have we really established a causative link such that we believe we understand the mechanism of the experiment? So the way we did that is that we did an ablation study. And an ablation study is where you knock out elements of your design to see how the system performs, to understand. It's like you're building a bridge and you knock out some of the supports. And when the bridge fails, or you've knocked out a few supports and the bridge fails, those links were really important and they're probably what was holding up our bridge, right? So a lot of studies you'll see in computer science, good studies will have these ablation studies. So we did things like we looked at the uniformity of the indices, how well they are spread among that means how well they're spread among the 12 qubits. And we found that topologies that involve all 12 qubits lead to higher connectivity. So, that there seemed to be a direct link there. And high uniformity also led to something called parity balance. So parity is a conserved physical quantity that we know essentially states that you can't create an electron out of nothing. So it's very related to energy conservation. However, it's slightly different in that you can create, for instance, two electrons, an electron and a positron. So it allows for things like that. So it's slightly different. This parity balance leads to energy level repulsion, which is the statistics that we're looking at. We saw that was a marginal correlation. So that implies that it's a necessary but not necessarily sufficient type of relationship. And then finally, we found that level repulsion, the statistics, so this is very well characterized, did indeed lead to a chaos signature, the kind of signal, the actual received signal that we wanted. So we did this type of causal ablation, and I believe it's really important, even when you're, it's not enough just to do vibe coding. You really have to go vibe code something or do something with agentic coding, and then perform these ablation studies. So you have to understand how your system works, right? Okay, so in our original study, we looked at designing these systems for the Willow quantum chip, which is a chip from Google. We actually we showed in our paper that, and we compiled using their public compiler to actual quantum gates that we could how many gates you would need to expect, what kind of fidelity, what kind of signal to noise ratio you would expect. And we found that for the systematic target that you would want, m equals 25, it's kind of getting to the limit of the hardware. And actually, Google released a new system called Sycamore recently, which we're investigating getting access to Sycamore, which has something, as you work with these quantum computers, they all have different error rates. And so you'll say like a qubit has a 95% error rate. So 1 out of 20 times, the signal will just be washed out. So this is the life of a quantum computer scientist. Okay, and I think I'm coming on my last few slides. Yeah, okay, this is my last slide. So what we did then is that we ran on the AQ2 IBEX, the 12 qubit system. And what we're just starting this. This is work in progress. We designed an RL compiler to create these quantum circuits. So you can naively create a quantum circuit using something called the Jordan-Wigner convention, or you can again use reinforcement learning to design your circuit. And so we're showing some benefit on the M14. I think for M25, the results are still we're still working on that to get a better result there. But studies are very early. This is results on running on actual hardware. And we like the AQ2 IBEX because it's trapped ion. So it's not like the Google Willow processor, which is on a grid. It's superimposed on a grid. So you have to, in order to have an operation with qubit 1 to qubit 12, you actually have to walk the Manhattan distance on the grid, which is not great when you're trying to do these all-to-all type of operations. Okay, so yeah, so I think one takeaway is we like the AQ2 IBEX. They're based out of Austrian Alps. And yeah, there's tons of new physics to be investigated. And we're really excited about the future of quantum computing because these machines will only get better. Their error rates will decrease. Actually, the AQ2 IBEX has a successor called the Forte, which we're queued in access for. And the Forte has a much better, has a 98% compared to a 95%, which is a tremendous leap for us because when you're running, as you saw in the past slide, you're running these circuits that are 262 gates. Each operation that you do incurs that error penalty. So it really is this compounding error. So that number is the error rate of the quantum, the qubit is very, very important to performance. And that's my last slide. And yeah, so thank you for your attention.
Amazing, thank you. I've got to say, it's honestly, Leonidas, so I don't even know where to start with that. I'm already getting WhatsApps from people asking to be connected with you.
Yeah.
So yeah, I'm going to jump into the questions. Thank you very, very much for that. I'll start with the first question from Johnny Williams. This is great, Leo. I have a solution, a quantum branch engine, a quantum-inspired decision intelligence architecture that uses decision compression and supposition modeled branching to explore multiple solution paths simultaneously rather than relying on actual quantum hardware. We use deterministic reasoning and inference-style filtering to prioritize optimal outcomes for modeling, discover onboard autonomy and distributed decision systems such as CubeSat, swarms, and environmental sensing. From your perspective, what are the biggest technical limitations preventing quantum-inspired architectures running on classical hardware from achieving practical advantages today, especially for distributed autonomous systems and real-time decision compression? That was, again, that was the question from Johnny Williams.
Yeah, fantastic. So there's this idea is that there's a tug of war, just to put this in context, is that whenever there's a, I'm neutral. I'm Switzerland in this debate. I'm only interested in what it can. I'm interested in applications, so I'm interested in figuring out this problem. So whatever can help me get there, I'm happy to investigate. But also, certainly, there's this larger context where one of the promises of quantum computing is that through things like it would break, for instance, public key encryption, which is based on SHA-256 hash encryption by using something like Shor's algorithm. This has been known for a very long time. However, it's like traditional computation. It's just been such a rich path, and there's been so many applications that you can develop. But we aren't like anti-GPU. You can see in our study we used GPUs, right? We couldn't do our study to do the rapid diagonalization in our RL process without GPUs. So we run on GPUs, and it's just like we've seen, in markets these days, the advance of GPUs has led to a tremendous advance in CPUs also, right? The CPU market, whether, or maybe not even x86, we have ARM type architectures now, but more von Neumann architectures that has lifted also, right? So I expect it's just like an economy, right? Where there's more innovation, there's more trade, it leads to more productivity, to speak in a more general term without losing some semantics, hopefully.
Brilliant, thank you. The next question comes from Christine Martin. Curious, in context of quantum entanglement, how does a wormhole affect the space between the two entities?
Yeah, no, so the idea is that, yeah, no, this is, I'm just kind of deciphering the work of Juan Maldacena and Leonard Susskind. So they really believe, and so there have been recent papers also, for instance, the idea is that, is there really a wormhole that connects those two quantum states, that there really is a traversable wormhole, which means that things can go through its kind of own personal space-time that connects these two qubits. So one study that I saw recently, I think it was published in March, is that they looked at the simplest entangled state. And I put this in quotes because this is the simplest entangled state is something that we all know. It's a hydrogen atom. So a hydrogen atom is a proton entangled with an electron. I don't know if people realize this. This is something we learn in your first semester quantum mechanics, right? And we study the system. It's one of the simplest systems. So, entangled quantum states are all around us. However, I want to put it in air quotes. So in this study, what they looked at is, if there really is a traversable wormhole, and there's this debate on, is it traversable? Is it like a wormhole that things really go through? Or is it kind of like a virtual wormhole, whatever that may mean, where it just has, I don't know, this wormhole that is hidden from nature that you would never see? And what they looked at is that they looked at the fine structure constant, which is the splitting of the energy levels due to the quantum entanglement between the proton and the electron. And they said that if there really is a wormhole, then some of the electric field from the electron would leak through the wormhole. And that would cause a perturbation in the fine structure constant. Because we know the fine structure constant is something like 12 significant figures. So it's something that it's a very well characterized success of physics that I think in my undergraduate laboratory, we measured the fine structure constant because it's such a well-known system. And so they reported a negative result that no, the fine structure constant that we all know and love from, over 70 years now is as it is. So there's no weird, exotic, traversable wormhole physics. And then I want to put a few question marks on that because it's such like an enclosed system. The hydrogen, the proton, and the electron, like they're so already tightly bound. It's a very shielded system. It's perhaps the most shielded system because you can't get anything more too fundamental than a proton and electron next to each other. That it's kind of like, well, yes, that's an entangled system. Practically, we would view them as one. You practically view them as one system. It doesn't strike us as a realistic system, quote unquote. However realistic, any of these quantum mechanical systems are, right? So yeah, I would say that's kind of like it's an open question. Physicists are still interpreting it, and people are designing new ways of testing whether this is a traversable wormhole. Certainly that Nature paper, which everybody hates, is I can say that without stepping on anyone's toes, I think, is claimed a traversable wormhole, but that sort of has been walked away.
Thank you. And I'm going to go on to the next question from Risto Mikulainen. Have you thought about using evolutionary optimization instead of RL? Because it is population-based, it is more robust against local minima and explores significantly more. The modern versions work in billions of dimensions. Oh, sorry, that just scrolled on. The modern versions work in billions of dimensions and at very large spaces, e.g., 2 to the power of 2 to the 70.
Yeah. So who asked that question?
That was Risto Mikulainen.
Oh wow, yeah, thank you. So that's exactly a great question. And I think, may I speculate on what may prompt this is, so Google had a paper recently where they used I don't know what they call it now, their Alpha Zero system or their Alpha Learn system. So they use that. They claim they have a system that uses evolutionary. They're kind of Alpha Evolve. Sorry, it's Alpha Evolve. That's the name of it. Their Alpha Evolve algorithm to design their what we showed in the last step is that RL step. And so yes, so we did this RL. Frankly, I showed the results. We're not very satisfied with them. We save about 2 to 5% in the qubit, the 2 qubit gates. So we hope to get to higher. We're designing an Alpha Evolve. So the wonder of agentic coding is that we can start quickly reproduce published work, and so Alpha Evolve is published, and they have their paper, which is on molecular spectroscopy using Alpha Evolve. They publish that, so we can try to quickly replicate it with our resources, burning those tokens. So you know how it goes. You just gotta they really got us, right? Those we're on the token treadmill, right? So yes, that's absolutely a good direction.
The next question is from John Thomas Foxwell. Sorry, a comment from James Cape. I could really use a Quantum 101 session for sure. And then the question from John Thomas Foxworthy. If quantum computers are so unstable, why do companies keep investing in them? What's the realistic timeline for reliability? For a quantum decision point, a single qubit to actually be useful, what conditions have to be true at the same time? And how close are we to hitting all of them at once? Essentially, what does ready actually look like?
Oh, wow. Yeah, that's like a fantastic slate of questions. Yeah, so let me take one is we got to give some credit, and I would say I'm a user, right? So I use these systems. So I can describe my practical experiences with them. So I credit them is that they're in the cloud now. I didn't have to provision, I didn't have to colo a quantum computer, which I much appreciated because I dislike co-locating things. It's always like this giant headache. Sorry, Lawrence. I don't know. Lawrence probably who works with all this. No, yeah, it's nice to have your colo. It's nice once you get it set up, but like you want to set it up once and not have to do it when there's a new machine. So yeah, they do exist in the cloud. So that's definitely some sort of milestone. In terms of usability, we're running experiments on them, but I think I didn't taking a very optimistic outlook. I didn't stress that 95% is kind of like it's too low, right? So the IBEX is really science project. I mean, luckily this is a science project, so it's sort of appropriate. But yeah, it would be tough. So I didn't underline this is that you don't run a program once in a quantum computer. So we're running 300 shots. So you run it 300 times. Everything is very statistical. So the experiments we're running are 300 shots each. So we're running each of those data points is actually 300 experiments, and then we're collecting statistics from that experiment. So and then yeah, I think there are all sorts of to the even the previous question is I liked it. I mean, I like it kind of because you have to practically be a physicist to engage in this hardware, and so that's a limitation, right? For better or worse, right? Is it reasonable to expect everyone to have some sort of this physics training? And it's really funny when you read these quantum computing textbooks, they try to abstract it, right? Like there are some textbooks that are like, okay, we're just going to teach you some physics. And I know you're a computer scientist, but we're going to teach you some physics. And other ones are like, okay, we know you're a computer scientist and you don't want to learn any physics, so we're going to try and do that. So I think practically that second approach is not tenable when you actually start working with the hardware as it is now. And so this is definitely the era. This phrase is NISQ, intermediate scale quantum hardware. And so I think what that encapsulates is that yes, you have to be a sort of physicist to work with this hardware right now, and that's a limitation. And when we exit out of the NISQ era, then we'll perhaps enter in a more golden age of this hardware. And what would it take? It takes I think Demis Hassabis, he's you got your neighbors in London. Do you mind? For a majority of you is yeah. So he's trying to make science like computer science, in that you have rapid. I think the success of computer science is you have rapid experimentation, absolute verification, because you can just run the computer program. Maybe AI has weakened this a little bit, but I think it's better, and a lot of open source, right? So I can easily port my experiment to someone else's experiment. And so, yeah, so once you see science becoming like that, which I think DeepMind is on this mission that I fully support, maybe we'll see a sort of a renaissance in quantum computing. Yeah.
Happy to make the introduction if you want.
To meet Demis?
To his team.
Oh, I met Demis, yeah.
Okay.
He's come over here. Yeah. He's
Okay, cool.
yeah.
I was going to say, I was going to say, they, I'm sure they haven't just let this slip by. What you're working on, it's incredible.
Yeah, Google, yeah, certainly has a big.
Yeah. I was going to say that
Yeah.
I'm sure they're all knocking on your door at the moment.
No, not at all. But yeah, sure.
With regards, okay, so sorry. With regards to the next question, James Cape, please to talk about the progression of the processing technology needed to achieve stable quantum computing. First electrons, moving photons. What's next?
Yeah. So the substrates. I think the first part of your question is the substrates, and yeah, it's there. I see three classes. So there's superconducting junctions, which are essentially Cooper pairs put into quantum states. There's trapped ion, which are I don't know, kind of like well isolated ions. So for instance, calcium. And then there's three. I think there's something called neutral atoms, which I'm a little less familiar with, but is possibly closer to physical interpretations and perhaps too much physics. So yeah, I think people are evolving that, and that's a very physics-based. I attended the Stanford Quantum Computing conference here, and there was certainly novel work on that. The other thing I should mention is that there's this that's related to this topic of error correction, right? So quantum error correction is so you have a split between something called logical qubits and the physical qubits. So the physical qubits, as I mentioned, are like these actual calcium ions, and it's just like a giant headache, right? Like you don't want to deal with this. Typically, I mean, I think actually like the Google team, they give talks where like, oh, we were running a supercomputer so large that we had bit flips and we dealt with this, right? And that's like sort of amazing that they're working at that scale. Yeah, for when you're in quantum computer, everybody has to deal with that. Even anybody, your solo practitioner has to deal with that. So that isn't good. And there are all these papers on quantum error correction, including using AI methods to do better quantum error correction, designing. So you essentially some quantum error correction, you have a group of qubits that have built-in error checking. So instead of you use like 5 or 6 qubits in a sort of scheme, and that gives you that sort of, it's almost like a RAID drive, right? Like you have, when you're in like RAID 3 or something like that, you have like 4 stripes. RAID 4, you have 4 stripes. And you just use 4 drives to make sure you have one really good drive. So that's sort of what quantum error correction is. And so that there's sort of a golden age of, there's one golden age of algorithmic design there. So that's like a algorithmic push. And yeah, we hope that improves because, that's a great, if you're a new computer scientist, that's a great topic, and you're really excited about algorithms. That's a great topic because it treats a real pain point. Yeah. So, and the third point I would make is just like transformers, it was an algorithm that really fit with the GPU. There's probably going to be a hardware evolution that really fits the quantum error correction, right? So this idea of co-designing the hardware with the algorithm, the computational layer, there's probably some really solid breakthrough there. And speculation on my part, but that would be intuitive answer. Oh, Lawrence, I think you're muted.
I am muted. Yes, thank you. I was going to say I'm very, very conscious of time, so I'm just going to say my bit at the end, and then what I'm going to do. If there's any other questions, I can see Christine. If we run out of time, Johnny. If we run out of time, we're going to post these questions to Leonidas on the Round platform, and Leonidas would be great if you could address when we have time. But when you have time, apologies. But again, it's to your testament, Leonidas, another like amazing presentation. So again, I'm hoping we can expand on this. But I just want to say honestly, like a huge thank you to you for this, and a huge thank you to OVH Cloud, the team at OVH Cloud. And again, guys, I just want to be clear, we are going to be doing a lot more like in-person events. We are looking, and I want to be completely transparent with you. Ideally, I'm thinking that we do events at the Rosewood. Ideally, the first one will be in September. We want to do it probably with about 10 founders, right? We want to see technical and non-technical founders like together. We don't want anyone who does not have a technical team, and we want people that are raising minimum $10 million. And I know it's been 6 years. Oh gosh, my phone went off there at the right time. It's been 6 years. We've never charged for anything. We are going to charge 3.75%, right, on it. And I want to be completely transparent with you. I'm going to get Tarek to send out a form to each and every one of you. If you want to be there again, please do fill out the form, arrange a time to speak with me. And we're going to work between now and September to get you up to scratch, to make sure that you are in a position to actually raise minimum $10 million. And then, of course, we will look to invite you out there with the VCs in Silicon Valley. So, yeah, Leonidas, I just want to say thanks again. Thanks once again for everything. I hope you enjoyed it. Again, brilliant questions from everyone. So thank you so much, guys. And yeah, apologies. I'm sorry that we ran out of time, but Leonidas, once again, thank you very much.
Thank you, everyone. Yep. Take care.
Guys, thank you very much. And if I don't see any of you, have an amazing summer. Thanks, guys.
Cheers.
Thanks, Lawrence. Thanks, everyone.
Thanks, guys.